Stationarity and Augmented Dickey-Fuller Test, a beginner's guide. Welcome! In this lesson, you will learn how to check if a time series is stationary. You will also try the Augmented Dickey-Fuller (ADF) test in Python. We will use real weather data to understand these topics with simple code and friendly steps. Running the cell now. Let us get started with some quick setup. Let us set up and load real weather data. First, we ignore any warnings to keep things clean. We load daily minimum temperatures from a real dataset. We import pandas to help us handle data. This is the link for the weather data CSV file. We read the CSV and make sure dates are recognized correctly. Let us print the shape. This tells us how many rows and columns we have. This line shows the first few rows so you get a sense of what the data looks like. Running the cell now. Notice how pandas quickly helps us bring in real-world data. Try changing the URL to see what happens with different datasets. Let us do a quick check. We are making sure there are no missing values in the data. This counts missing entries in each column. Running the cell now. Clean data helps prevent errors later. Now let us see what the data looks like. Here we make a simple line chart of the daily temperatures. We import matplotlib, which is a tool for plotting charts. This sets the size so it is easy to see. We plot dates on the x-axis and temperature on the y-axis. A title helps you know what you are seeing. The y-axis is labeled for temperature in Celsius. We label the x-axis for dates. This line actually draws the chart. Running the cell now. Notice how the temperature changes over time. Try making the chart bigger or smaller by changing the fig size. What is stationarity? A stationary time series stays stable over time. Mean and variance do not change as you move along. If trends or seasonality exist, the data is probably not stationary. Why does this matter? Many forecasting methods only work with stationary series. Running the cell now. Let us look for stationarity in our temperature data. Let us see if our data is stable by checking mean and variance. We check how the mean and variance change by using a rolling window. Here, the window uses about a year of data at a time. This calculates the average within each window. This does the same for variance, which measures spread. We make a plot to see these changes. The chart shows the original temperatures. The rolling mean line shows how the average shifts over time. The rolling variance line shows how the spread changes. We add a legend to tell lines apart. A title helps remind us what we are seeing. Now we actually show the chart. Running the cell now. If the blue and orange lines move a lot, the series is not stationary. Try adjusting the window size to see what changes. The Augmented Dickey-Fuller (ADF) test. The ADF test is a standard way to check for stationarity. It gives a test statistic and a p-value. A low p-value, usually below 0.05, means the data is probably stationary. You do not have to do the math yourself, Python can handle it. Running the cell now. Let us run the ADF test on our weather data. Now let us use the ADF test. We are going to import the ADFuller test from stats models. This line runs the test on the temperature column. The result includes several important numbers. This prints out the ADF statistic, which helps judge stationarity. The p-value tells us how likely the data is stationary. Here we loop through some standard thresholds, called critical values. We print each critical value and compare it to our test result. Running the cell now. If the p-value is low, that usually means the data is stationary. Try running this test on another column if your data has 1. Let us make the ADF result easy to understand. This block gives a friendly verdict based on the p-value result. If the p-value is less than 0.05, the data is probably stationary. This message summarizes a likely stationary situation. If not, we say the data is likely not stationary. This message points out when the data does not pass the stationarity test. Running the cell now. Stationarity can make forecasting much easier. Practice explaining this result out loud like you would to a friend. Why would a series not be stationary? Non-stationary data often has a trend or seasonality. A trend means values go up or down overall. Seasonality is a regular pattern, like higher temperatures each summer. Next, we will try to remove these effects. Running the cell now. Let us see how to make a series stationary. One common technique is to difference the data. We use differencing to remove simple trends or patterns from the data. This line creates a new column with each day minus the previous day. Now we make a line chart to check how it looks. We plot the difference data over time. The title helps you know this is showing changes, not raw temperature. Now we display the plot. Running the cell now. If the plot looks more stable, differencing helped make the data stationary. Try viewing the difference twice by chaining difference again. Let us see if our new data is stationary now. We import NumPy to help with numerical tasks. Now we run the ADF test on the difference data. We drop any missing results caused by the difference. This prints the new ADF statistic after differencing. This prints the new p-value for the difference series. Running the cell now. If this p-value is now below 0.05, the series is likely stationary. Try differencing again if the p-value is still high. Let us try to remove yearly seasonality with seasonal differencing. Seasonal differencing subtracts the value from a year ago. This helps remove repeating yearly patterns. We set up the chart size. We plot the new, seasonally difference series. A title shows this chart uses a shift of 365 days. We show the figure. Running the cell now. Seasonal differencing is powerful for regular patterns. Try changing the period to match patterns in other datasets. Let us check if the seasonally difference series is stationary now. This runs the ADF test on the new column with seasonal differencing applied. Now we print the updated ADF statistic. We also print the updated p-value. Running the cell now. If the p-value is low, we removed enough patterns to get stationarity. Try using different differencing values and see how the result changes. Useful tricks: log transformation. A log transformation can help make variance more constant. This is useful especially if peaks and dips grow over time. Let us try it out. Running the cell now. We will see if this step makes the series easier to model. Now let us see what happens when we use a log transform. We make a new column with a log transformation. The +1 makes sure we do not try log of 0. This helps smooth large jumps in the series. We set the chart size for easy viewing. We plot the new log temperature series. The title makes it clear this is now log transform data. We show the result visually. Running the cell now. Log transformations can help many time series. Be careful, use only when all values are non-negative. Now let us put it all together, log transform and differencing. We create a new column that is the difference of the log transform temperature. This combines both variance smoothing and removing trends. We set up the chart to look at the combined effect. We plot this new transformation over time. The chart title helps you know exactly what you are seeing. We show the final visualization for this data step. Running the cell now. Combining these methods often helps many real-world data sets. Try to guess if the new line looks more stationary than earlier ones. Let us run the ADF test one last time on our best transformed version. This runs the ADF test on data that was log transformed and differenced. This prints the new ADF statistic for the best process series. This prints the new p-value for the best process series. Running the cell now. Stationarity transformations are often needed before using advanced models. Keep practicing with different transformations to build skill. Let us try a mini project where you choose the differencing period. Here we prompt you to type in the period you want to use for differencing. 1 means each day, 365 is 1 year. We turn your answer into a number. We create a new column that is the difference between each temperature and the value from your chosen period ago. Let us set up the chart window. Now we plot your custom difference data. We title the plot so you see which period was used. We add a legend for clarity. Now we display the customized plot. Running the cell now. Try the ADF test on your new column and see if you achieved stationarity. Share your results in the comments or with a friend for feedback. Let us finish our mini project by applying the ADF test on your new series. We run the ADF test on the column we just created with your chosen period. This prints the ADF statistic for your custom difference. This shows the p-value for your custom difference. Running the cell now. Try other periods and compare how the ADF results change. Experimentation is how data scientists learn what works best. Troubleshooting common problems. If you see errors, check for missing data or try a smaller period. Remember to drop missing data using .dropner before running the ADF test. If your p-value does not go low, try both differencing and log transforms together. Running the cell now. Go back anytime if you need to review how to fix these common problems. Now let us try a challenge. We ask you to paste a link or a file path to your own CSV file containing time series data. Your input will be stored in the variable called file. We attempt to read your file using pandas. We print the first few rows to check that your data loaded correctly. If it does not work, we print an error message. This line gives you a clear tip to double-check your path or link. Running the cell now. Try this challenge and see how the stationarity tests work on your own data. Once you finish, give yourself a pat on the back for exploring outside the lesson. Recap: what did we learn? You learned how to load time series data, visualize and check for stationarity, use the Augmented Dickey-Fuller test, transform data for better forecasting, debug problems. Great job! Stationarity checks are now part of your data science toolkit. Running the cell now. Try reviewing other lessons to connect these skills to models like ARIMA. Next steps: keep learning and share. Practice stationarity tests on new datasets. Share your results with the community or in the video comments. Like and subscribe if you found this lesson helpful. Happy coding! Running the cell now. Try a minute project, find a new dataset and see if you can make it stationary. You are building real data science habits. Come back soon for more lessons.